Hello everyone, my name is Ace Garrett, BSE second year student, and I'm here to solve 3 numbers for electrical circuits 2. So this is number 1, so the first thing we have to do is actually look at the given first, because we'll have to convert them, because this is in vector form. So 10, so Z1 is equivalent to 10 J15 ohms. So if we convert that using a calculator, so it will equate to 18.0278 angle 56.31 degrees ohms. So that is our Z1. So this form is what we'll be using for the whole number. So Z2 is equivalent to 6 minus J6 ohms, so that will equate to 10 angle negative 53.13 ohms. So also for the current, we'll also have to convert it, so 15 angle 10 degrees amperes. So now that's out of the way, the first value we have to solve is the total impedance. So the solution so the formula for total impedance is ZT, total impedance, is equivalent to 1 over Z1 plus 1 over Z2 multiplied by the power of raised to the power of -1, so both of them. So for this to properly work for our problem, we'll have to simplify this equation, this formula. So it will become Z2 plus Z1 over Z2 times Z1. So I just multiplied it so that it will be this form. So now we'll have to invert them because of the -1. So the power -1 is not here anymore because we used it. So this is the formula that we'll be using. So we'll have to substitute our numbers. So Z2 is that 18.0278 angle 56.31 times 10 angle -53.13 degrees over sa Z2 and Z1. So 18.0278 angle 56.31 degrees plus 10 angle -53.13 degrees. So if you use your calculator properly, the total impedance will equate to 10.3227 angle -20.45 degrees. So we need to solve the voltage because we'll be using it to solve for the power factor, total power factor. So not the gonna use it for the total power factor, so we'll also solve it. So the formula for total voltage is I total times Z total. So our I total is 15 angle 0 squared, 0 degrees. So we'll put that, and the Z total is this, the one that we just solved earlier. So 10.3227 angle -20.45. So that will equate to 154.8399 angle -20.45. So now we are gonna solve for the current because we have all the values for the impedance. So this is current division theorem. So it only applies to parallel circuits. So this is the formula that we'll be using. I1 is equivalent to I total times Z2 over Z1 plus Z2. We have all the values, so all we have to do is substitute. So our I total is 15 angle 0 degrees times 10 angle -53.13 degrees over 18.0278 angle 56 plus 10 angle -53.13. So that would equate to I1 is equivalent to 8.5890 angle -76.76 degrees. So we'll have to solve for the I2 now. I2, they have a similar formula. Oh no, not a similar formula, because this is Z1. I think. Oh no, this is Z2. Oh, I was wrong here. So you have to use the Z2 here. You have to use the Z2 here. But I still use the Z2. I just wrote the wrong number there. And for the I2, you have to use the I total times Z1 over. So you have to use the Z1 here over Z1 plus Z2. So our Z1 is 18.078 angle 56.31. So that will be over our Z1 and Z2, which is 18.0278 angle 56.31 plus 10 angle negative 53.13 degrees. So if you equate that with your calculator, it will equate to I2 is equivalent to 15.4840 angle 32.68 degrees. So now that we have our currents and we also have our impedance, we can solve for the power. So the formula for power is P1 over I1 squared R1. So as you can see, we don't have R1 here, but the value for R is can be found in the impedance. So our R1 is the 10 in the Z1 impedance. So this the real part of the impedance impedance is the resistance, so 10. So this will also be our R2, the number 6. So we have all the variables needed to solve this, so we have to substitute. Our I1 is 8.5890 angle negative 76.76 degrees squared times 10, our resistance. So we have to equate that. It will come up to 737.71 angle negative 53.52, but our answer will only be the 737.71 watts because this is only the direction. So our answer is this, but you can also put that if you want. So the P2, we just like what we did to P1, our R2 is the real part of the impedance, the Z2. So we have to substitute 15.4840 angle 32.68 squared times 6. So if you calculate that, it will come up to 14.38.53 angle 65.36. So that is P2 is equivalent to 14.38.53. Again, this is just the direction. So that is the power and the power 1 and power 2. So let's solve for the power factor 1. So the formula for power factor 1 is cos theta is equivalent to R1 over Z1. R1 is given, right, because it's 10, and our Z1 is also given by the question. So 18.0278 angle 56.31 degrees. So if you calculate that, it will come up to 0.56. So our power factor 1 is 0.56. Also with the power factor 2, cos theta is equivalent to R2 over Z2. Our R2 is also given and our Z2 is also given. So 6 over 10 angle negative 53.13 degrees. So if you calculate that, it will come up to 0.6. And then for the power factor total, this is why we solve the total voltage, because we use it for the power factor total. So the formula for power factor total is cos theta is equivalent to cos minus 20 cos theta. So our theta that we'll be using here is the one in the voltage, negative 20.45. So this is the main reason why we solve the voltage total, so that we can solve the power factor for power factor total. So it will equate to 0.94. So we also have to show the vector diagram. So the vector diagram isn't actually that hard to understand, because these values, the 56.31, 32.68, 0, these are the directions or the imaginary part of our Z1, Z2, I1, I2. So example Z1 56.31. So that is the direction of the Z1, and this 32.68. So that is the I2. So our I2 is I2 is 32.68. The I total is 15, or 15 angle 0 degrees, so it's 0 degrees. Our V total, which is negative 20.45, is here negative 20.45. Our Z2 is negative 53.13, just like here. So we put it at the fourth quadrant because it's negative. And the I1, which is negative 76.76, which is here negative 76.76. So that is the vector diagram. You just have to graph, you have just to pinpoint in a Cartesian plane where the directions are going. So this is number 2 of the activity. So this is the question. Two impedances Z1 is equivalent to 8 plus J6 plus Z2 equivalent to 3 minus J4 are in parallel. If the total current of the combination is 25 amperes, find the current taken and the power consumed by each impedance. So we, just like number 1, we have to convert from the vector form. So this is the vector form, so we have to put it here. So Z1 is equivalent to 8 plus J6 ohms is equivalent to 10 angle 36.87 degrees ohms. And this Z2 is equivalent to 3 minus J4 ohms. So that will equate to 5 angle negative 53.13. And the I total, which is 25 amperes, there is no direction given, so we'll just assume it 0 degrees. So the formula we'll have to use is Z total is equivalent to Z1 times Z2 over Z1 plus Z2. So both Z1s and Z2s are actually given, so we can substitute them. So Z1 will be 10 angle 36.87 times 5 angle negative 53.13 over the Z1 and the sum of Z1 and Z2, which is so we'll write 10 angle 36.87 degrees plus 5 angle negative 53.13 degrees. So if you use your calculator correctly, it will equate to the Z total being 4.4721 angle negative 26.56. And then we'll solve for the I1. Now that I1, we can solve this because Z1, Z2, and I total are given, just like number 1. So this is the formula: I total times Z2 over the sum of Z1 and Z2. So we'll have to substitute. So 25 angle 0 degrees, which is the total current, times 5 angle negative 53.13 degrees over 10 angle 36.87 plus 5 angle negative 53.13 degrees. So if you use your calculator correctly, it will equate to I1 being 11.18 angle negative 63.42 degrees. So we'll solve for I2. So its formula is actually just the same, but the Z2 and Z1. Right? So if you're solving for I1, you have to use Z2. If you're solving for I2, you have to use the Z1. So that's the main difference. That's the only difference, I guess. So I total times Z1 over the sum of Z1 and Z2. So we have to substitute the I total, which is 25 angle 0 degrees, times 10 angle 36.87 degrees over 10 angle 36.87 degrees plus 5 angle negative 53.13 degrees. So if you calculate that correctly, it will equate to 22.3607 angle 26.57 degrees. So now that we have both I1s and I2, and we also have the impedance as given by the question, we can solve for P1. So P1 is equivalent to I1 squared R1. So R could actually be found in the impedance formula, the real part of the not impedance formula, impedance value, the real part is the real part of the impedance value is the resistance. So I1, so we'll have to substitute again. So we just solved that I1 is equivalent to 11.1803 angle negative 63.43 degrees, so square that because that's in the formula, times 8, which is 8 our resistance there. Look at this, 8. So if you equate that, if you calculate that, that will equate to 99.9 angle negative 126.86 degrees. So our power is actually just the 99.9. I rounded it up, which is 1000 watts. Because again, this part is just direction. So we'll have to solve for I2. I2 squared R2 times R2. So these are also both given because I2, we just solved I2, and I3, R2 is this part, 3. Oh no, yes, 3. The real part. And then this 22. So this I2 is equivalent to 22.3607 angle 26.57. This is not 0, that is degrees. Yes. Degrees squared times 3. So if you calculate that correctly, that will equate to 22.3607 angle 26.57. So our power value is also this, just this, the 22.36 amperes, because this is just direction. So we have solved for the current and the power taken each by each impedance. So we have solved I1, I2, I1, I2, P1, and P2. So this is P2. P2, sorry. So this is the last number, number 3. So we'll have to read the question first. Refer to the circuit of figure 14.10a and determine the resistance and reactance of the lagging coil load and the power factor of the combination of the currents as indicated. So this is the figure. The current is 4.5a, 2a, and 5.6. So there are 3 currents. So this is the whole circuit. So the first thing we have to do is solve for the impedance, so which is V over I2. So our V total is 300 and our I2 is the 4.5. We just use that 4.5. So equivalent to 66.67 66.67 ohms. And because this is a lagging coil load, so this is an RL resistive inductive circuit. So we'll have to use Z is equivalent to R plus G XL. So we have Z because we just solved it. So 66.67 ohms is equivalent to R plus G XL. So in this part, R is equivalent to Z cos theta and X is equivalent to Z sin theta. We just use we just look at an impedance triangle. So if you look at that properly in the impedance triangle, you can come up with these values. So the next thing we have to do is actually use a phasor graph or diagram to know what to do next. So this is a parallelogram, so just never mind the length, you can understand it. So this line is the 56.6 amperes, this is the 45.A, and this is the 2A. So this is alpha and beta. So you can come up with the values, so you can assume them by looking at this phasor diagram. So A would be this 2A, and B would be for 4.5 this, and C would be 5.6 this. So you could come up with this A, B, and C if you use a phasor diagram, a phasor graph. Okay, so we'll have to use the cosine law, which is B squared is equivalent to we'll have to use the B because I want to solve for the beta. So you can use any other, if you want to use the alpha or the beta, you can use it, but I want to use the beta. So B squared is equivalent to A squared plus C squared minus 2AC cos beta. So we'll have to rearrange it to solve properly for the beta, which is cos beta is equivalent to b squared minus a squared plus c squared over negative 2ac. And we have all the values for a and b's, a, b, and c, so we can substitute. So our b is 4.5 squared minus 2 squared because our a is 2, and 56 because our c is 5.6 squared over 2 over negative 2 times 2 times 5.6 because that's 2ac, negative 2ac. So our if you calculate that using your calculator, you'll come up with a cos beta is equivalent to 0.56 degrees, or the beta would be equivalent to 47.93 degrees there. So going back to the formula that we got from the impedance triangle, which is r is equivalent to z cos theta and x is equivalent to z sin theta. We got that from the impedance triangle. So because the angle that we solved for in this part is the beta, so we'll just have to do minor tweaks to our formula. It really doesn't make any change because you can use any angle you want. So r is equivalent to z cos theta, beta instead of theta. It really doesn't make any difference. We just solve for beta. So we have solved the z early on. This is the 66.67. So we have to substitute that 66.67 times cos beta is equivalent to 0.67 here. So cos beta. I just placed the number. So to save time. So 0.67 beta. So if you calculate that using your calculator, it will equate to R is equivalent to 44.67 ohms. So for the X, so that will equate to Z sine beta. So, oh, I am wrong. So that will equate to 66.67, which is sine. So what's that? 47.93. So if you use your calculator, 66.67 times sine 47.23 is equivalent to 49.49. So I just forgot to write the sign in my rewrite. So you can solve the power factor. The power factor is basically just cos beta, so it will be equivalent to 0.67, just like this. So if we rewrite the impedance again, so we use the R, which is 44.67, and J and the X, because this is lagging, because this is this R plus JXL, so our XL is equivalent to this J 49.49. So that is my answer for the three numbers given. Thank you for watching.